so nice to see that so many of you still have some energy left in you. Like it's the last day and it's the second to last talk and everyone's tired and overloaded and everything. So hello, my name is Stian and I'm from Norway, as Bodil said. That's that weird country like across the ocean where it's cold all the time and always dark. I work for an IT consultancy called Beck, as Bodil mentioned. There I do mostly web things. I help clients out with their various web needs that usually revolves around removing JavaScript and not adding more. But in my spare time, I enjoy exploring weird and unusual ways of programming things because that's fun and it teaches me useful things to use in my day job. Okay, so today I am going to show you a little bit of something called concatenative programming. Here we have a blank canvas and a blank output. It's pretty much every artist's worst nightmare, the blankness of the canvas. So we're going to fill it with something. If some of you are not familiar with the HTML5 canvas things, that's kind of what I'm doing here. So I just mapped it into a concatenative style. So don't worry. Is it readable? Can people read this, by the way? Yeah, it's nice. Good. All right, we have created a line. Yes, lines are useful and they're often nice to look at. But we don't want just a line, we want something more. So let's start from somewhere else, like here. Maybe we can do, oops, that's a long line. Do like this, and then maybe we do that, and final thing. Yes, now we have a square. Squares are nice. We can do things with the square, like we can draw a square many times. That's not terribly interesting in itself because you just get 10 squares on top of each other, so that's not very interesting. But if every time we draw a square, we do something exciting to where the square is. So we can rotate things, but now everything just slides off the canvas. That's not very good. So we have to do some tricks. And now we're rotating it around the center instead, because normally in computer graphics the 0, 0 point is up in the left top corner, and everything revolves around that point. So you have to translate it to the center and then rotate it and take it back. Okay, so that's not terribly interesting, but there's something cool we can do. That's called a neon effect, and for that we need some shadow color, and we need some blur things, and we need to, okay, this is the hardest part in my entire talk, to write this invocation correctly. Yes, nailed it. Trying to spell composite operation correctly every time is kind of hard. So what we can do is draw this in varying line widths. Of course, something broke. There we go. Now we have this glowing neon effect. That's kind of cool. So what if we also do, I don't know, we maybe take a random we do this. We get some cool, glowy, squarey, weird thing. Now we have something that actually looks kind of artsy-fartsy. And we've written all this code, and it looks kind of strange. And there's a backup slide. And what was that? That was strange, right? Well, that was concatenative programming. And concatenative programming, it's a style of programming. I'm not sure if I can use the word like paradigm for this, but I decided to go with the safe route and call it style instead. Oops. And in this style of programming, programs are constructed by composing functions. And this comes in like an opposition to what we normally do by constructing programs by applying functions to values. So concatenative is an alternative to applicative. This sounds kind of strange, so let me explain to you exactly what it is. So we construct programs by composing functions, as I said. And here's a program made of a composition of 5 functions. Anyone want to guess what this program does? No? OK. It checks if the successor of a number is divisible by 5. Totally clear, right? So this program, here it's a composition of 5 functions, and the composition is implicit, meaning that in a concatenative program, you don't actually have to be explicit about your compositions, because every time you put 2 functions next to each other, it's a composition. You can reintroduce the composition operator, but since it's actually every time there's a space, there's a composition operator, you don't really need it. You can like look at it from another angle, and you can see like pipes. And now it kind of looks like something you would write in a command line. And that's kind of interesting. But if you look a little bit closer, there's something strange going on here. If we write this program the way you would write in a C-style language or something, perhaps, with parentheses and stuff, you see something strange. Because surely 5 and 0 aren't really functions, they're values. So why are you invoking 5 and 0? That's not right. So the thing is, in concatenative language, there are no values. There are only functions. Like in a functional language, you can say that you have functions as values, but here you have values as functions. That's kind of weird. So that's the secret sauce of concatenative languages. And that's also why we are able to compose like this, because everything in the language is a function, and every function has the same interface. So the successor function is a function from state, the old state, to new state. And similarly with number 5, that's also a function from the state to the new state. So what the function 5 actually does, it modifies the state and returns the state again. And the world state can be anything, but usually it's a stack. And that's why these kind of concatenative languages also are often talked about as stack-based languages. But it doesn't have to be a stack, it can be. So that would mean you have this kind of functions instead. You take a stack in and you return a stack out. And that's kind of the interface for all the functions. It sounds kind of weird, so we're going to look at how it operates in practice. Here we have the program 5. The program 5, it puts a number 5 on the state or a stack. And if I do the program 510, you have a 10 and a 5 in the stack. Then I can do the program 510 plus, that's 15. And this program is equivalent to this program. That's kind of neat. You can do interesting things with that. So if I were to do the suc5 mod 0 equal thing, it obviously doesn't do anything because it kind of requires some pre-existing state to work. So if I put number 6 on there, this program results in the state being false. And what's actually happening here is, if I just take this part away, this kind of program, it takes the successor, it takes the stack, it takes the top element of the stack, it adds 1 and puts it back. And then you run the program 5, and the program 5 puts 5 on the stack. And if you then do the mod, you get the remainder of the division between the successor of 6 and 5. Then you can check that for equality with 0, and you get false. So if I put 4 in here, I get true, because the successor of 4 is 5, and 5 is divisible by 5, and that's nice. So that's how you would work with this kind of program. And this is also why many times people talk about concatenative programs being in the postfix notation. Some of you might have used one of those old HB calculators where everything was written in reverse Polish notation. It kind of looks like this. But the thing is, it's not actually an operator in the same sense as you would in a calculator. This is a function. So 4 is a function, and plus is a function. So this is just a composition of all the functions. The postfixness is kind of incidental, but it's nice to, it helps you to think about things if you use that kind of thinking. Okay, so this doesn't seem really expressive at the moment, but we can add expressivity by adding quoted programs. Or the quoted programs aren't actually quoted programs, they are functions adding quoted programs to the stack. This is a program that uses a quoted program. This is a filter. You can filter arrays looking for numbers that are less than 2. Or this little program, which takes the sum of all numbers in a list. It looks kind of nice. It's so small, and it's almost impossible to know what it does without knowing what concatenative programs do. You can also use quotations for control structures, such as if tests. And an if test will take 3 quotations off the stack and run the top one to produce a Boolean, and use the Boolean to determine which of the other 2 are going to be executed. And you can do the same with recursion. You can do anonymous recursion with this. This is a little program that will calculate the factorization of a number by using a linear recursive combinator. And combinators are, at least in concatenative world, the combinators are special kinds of functions that operates on this kind of quoted programs. So you can say that in a concatenative language you have functions and you have descriptions of functions. So you have both the ability to create a description of some kind of program and add to it and modify it and do all kinds of crazy meta-programming stuff if you want to. So all good, maybe. If you compare this program to its counterpart, this is written in F-sharp-ish syntax. I hope people are able to see what it does anyways. We can see what we gain by having this kind of style of programming. We don't have to do composition. You don't have to worry about arity of functions. Here you have to flip the arguments of the mod function in order to partially apply one of the operands. And also, if we didn't have auto-currying and automatic partial application, we have to do that as well. So you can see that if you want to have this kind of point-free style programming, being in this concatenative world is nicer because everything is implicit. But the thing is, you have to fiddle with the stack. If you were to implement this kind of mathematical formula in a concatenative world, it would look like this. And that's not very nice. The good thing is that we can hide that. We don't have to worry about that thing all the time. And we're going to look at how that would go about later. So there are obviously some benefits and there are some downsides, and you can wonder, like, why did someone bother to make this? Why did someone spend time envisioning this kind of programming style? And the thing is, at least there are 2 very distinct ways that this thing came about. We're going to look at it because looking at why something exists. It tells you a little bit about how you're going to use it. Okay, so the first thing we have is Forth. A lot of people have probably heard about Forth before. It's one of those languages that gets talked about, but mostly in a historical curiosity setting. It was invented in 1968 by this guy, Charles Moore, or Chuck Moore, as he usually goes by. And Chuck was really sick of the Tower of Babel. And the Tower of Babel was the name he used to describe the world of programming back then. Like he had to, when you were programming something on a machine, you had to think about, okay, you have a compiler for a language you're compiling, writing in, you have some sort of assembler, you had some sort of machinery to keep users from interacting with each other, because back then you used time-shared machines. And you know, all these sort of things that was keeping him away from his precious machine, and he really wanted to get back to that. And he wanted something simpler. So he made Forth. And Forth was supposed to be this really thin layer between the machine and the CPU and the programmer. And he also wanted to design this language so that it was portable and easy to implement. Because back then you had a lot of specialty machines and machines that were custom-made for certain kind of things, and he wanted to use this language all the time. So he usually carried with him a stack of cards that had the Forth compiler implemented on them, so you can just import them into wherever he went. That's kind of strange. So of course the stack became the natural choice for the program state, because when you're working with machine code, relying on registers is kind of cumbersome, because registers, they change a lot between machines. But all machines have a stack. So if you can avoid the registers and only rely on the stack, it becomes way easier to port the program from machine to machine. Yeah, so it avoided the whole problem of registers, and he was able to port this program to at least 19 different CPUs in his time. It was kind of crazy. But the thing is, the programming interface also had to be simple. Because if the programming interface was really complex, then the whole compiler for the language would also be complex, and the whole interface would be complex, and everything would just be too complex to re-implement all the time. So he used postfix. He actually used postfix, and he used it to avoid worrying about arity of functions. So if everything is postfix, you don't have to think about parentheses and stuff like that to limit your functions. Because in a postfix world, all the operator precedence is explicit, because yeah, all the operands are placed before the operator, so you don't have to worry about that. And also, he wanted it to be word-centric, so it was more natural for humans to work in this kind of language. So that's why everything is space-separated, and this also had a neat effect that writing a compiler for this kind of language became really easy, because you can just separate on the space. You can just read from the input, and as long as there's space, there's a new thing. So implementing your own Forth is, because of this, is really simple, and it's a great way to learn. But the thing is that optimizing for this kind of simplicity turned out to be a good thing for Forth. Forth has been and is still used with great success in a lot of embedded systems, because the compiler is really tiny, so there's not a lot of overhead in the compiler itself, so you can implement it directly on the hardware most of the time. And it's even hurling through space attached to a comet, because NASA love Forth, so they're using it all the time. And the thing is that it can also serve as both a low and a high level language. That's kind of strange, because you would think that operating so close to the hardware would mean you have to spend a lot of time worrying about hardware. But as you can see later, there are some really cool mechanisms in the way that a concatenative language works that makes it suitable for working on both a high and a low level. Okay, so Forth's concatenative style stems from purely practical reasons. This is another language called Joy. It was made by a guy called Manfred von Thun. He worked at a university in Melbourne, I think, La Trobe University. And he had some really strange ideas about programming. And he made his own language to implement those ideas. So Joy is a purely functional language. In Joy, everything is a function, kind of like the way I described concatenative style earlier. he was really inspired by Bacchus and his FP system from his paper about can programming be liberated from von Neumann architecture, and also combinatorial logic. So he saw that with this kind of system, you can eliminate variables and thus make programming simpler. So he implemented this in Joy, and that's where the term concatenative stems from. Because Forth didn't actually ever use that term. Forth was just Forth. But when this guy made Joy, we got this theory that we can use to talk about this kind of programs. Okay, so he landed on a simple syntax by way of implicitness. He saw that if he turns everything into a function, you can compose functions without having an operator because the composition is implicit. So that's why the syntax in his language is really simple. And also he chose a stack for the program state because a stack has simple semantics. You can only read and write to the top of the stack, and everything else is just handled. So that means you don't have to make a lot of strange functions to modify the world state. You just have to use like pop and dup and stuff like that. And he initially started with only 4 kinds of special functions, but that grew over time. Anyways, so Joy's take on concatenative style comes from a theoretical place. And that's kind of strange. You have one practical solution and one theoretical solution, both ending up in the same place. There are also some other concatenative languages out there. I'm not going to spend a lot of time on them, but I'm mentioning them anyways. You have PostScript, which was mentioned yesterday in Mariko Kosaka's talk about type. That's a neat language. Why they ended up with a concatenative style, I'm not really sure. They don't really say in the interviews and stuff, but they were aware of Forth because they said so. So I'm guessing that PostScript used the same reasoning as Chuck Moore, that they wanted it to be portable because PostScript was supposed to live inside your printer. So if you can port it from printer to printer easily, it's good, I guess. And then you have CPython virtual machine and the JVM virtual machine. That's redundant, I know, but yeah. And they also use, in their kind of intermediate language, they also use concatenative style because working on a stack, as it turns out, is really easy to optimize. You can easily do pattern matching and replacing large patterns with more performing patterns and stuff like that. So yeah, these virtual machines, they use stack-based languages. And you have Factor, which is probably the most industry-ready concatenative language to date. It's largely based on the same ideas as Joy, and Von Thun, before he died, sadly, he said that Factor was a worthy successor to Joy. And it's if you want to do concatenative programming as a day job, I guess Factor is the most suitable program. And also there's Cat and Kitten and Popper and many other small toy languages that tries to implement a type system on top of this again, and that's really exciting if you're really into types. And also there are various attempts at doing concatenative embedded DSLs, especially Chris Okazaki wrote a paper about embedding a concatenative DSL into Haskell, which also has some really interesting discussions about typing these kind of languages. So if you're into that, I would recommend checking that out. Okay, so back to this. We have 2 different points of view, one theoretical and one practical. And they largely end up with the same semantics. So clearly there's something about the semantics that are kind of useful, I hope. When we talk about programming languages and programs and learning about programming and stuff like that, we often hear this quote. A language that does not affect the way you think about programming is not worth knowing. That was said by Alan Perlis. And especially with this kind of weird language, you would wonder, like, what kind of strange sorcery do you learn from knowing this? And as it turns out, someone has already written the book about this. This book is called Thinking Forth. It was written by Leo Brody. It was released in 1984. And it has a subtitle called A Language and Philosophy for Solving Problems. And this book describes how Forth programmers use Forth in their day jobs and how they would approach problem solving in a very Forthy way. Okay, so this book, it was ahead of its time. They interview a lot of consultants working for clients, and I'm also a consultant, so when I read this book, I was thinking, like, well, that's the same problem as I am having. Like, the client can't decide what they want, so they have to redo the program. Okay, they did that in the 70s and 80s, and they're doing it now. So how little have we progressed? So there are some striking similarities to extreme programming and the agile movement in this book. They talk about things like refactoring and many things that later became popularized through these movements. And sadly, this book wasn't widely read, so missed opportunity, I guess. And also, it draws a direct line between how Forth is designed and all the thought that Chuck Moore put into it and how Forth programmers end up working. That's kind of special. There's not that many books that draws this kind of direct line between a design of a language and how the users of the language used to solve problems. That's kind of interesting. So, yeah. So it focuses on simplicity in the work. There's an actual quote from the book here. If you don't understand a problem, you don't understand a problem until you can simplify it. So there's a lot of focus on simplicity all the time, and this probably stems from the simple semantics and also that Chuck Moore was so prolific in his search for more simpler ways to do things. And the thing is, in this book, they talk about how you would achieve simplification through layering. And this is kind of special because I talked about, as I mentioned earlier, that that Forth can be used as both a high-level and a low-level language. And this kind of layering thing is what's enabling that to happen. So layering is achieved through something they call factoring. And factoring is a continuous process of evolving software. The Forth programmers, they work in cycles, most very similar to what you call like the agile cycle, where you build something that kind of works and you analyze it and you refactor it and you move on. And to factor, they identified some kind of rules for when you should factor things. And one of them is to clarify meaning. So whenever you feel like you need a comment or something to describe what this is doing, you can factor it and make what the program does more clear. You can factor to give something a name. If a particular function represents something that is central to your domain, you can just name it that and go about your day. You factor to avoid repetition, which is basically dry. And this is 1984, so it's probably like 15 years before Ruby came around. And you would factor to hide details that are likely to change, so you don't leak configurable values throughout your program, I guess. And also, you would factor to simplify APIs. If you have an API, especially like working in a concatenative language, you always have to worry about what's on the stack. So if you have to shuffle like 4 values on the stack, that's bad. That's a hard API to work with. So you can simplify that. That would be good. And the process of factoring creates a layer of special vocabulary that supports the next layer. So if you were, for instance, to create a text editor, you would maybe start with cursor position. You can create a special vocabulary for working with cursors, and how that actually translates to the screen and stuff. It's hidden behind the API. So when you have this kind of layer to work with, you can then make something more complex without having to worry about all the details below. And this sounds kind of obvious now because we have become better programmers. We have worked with a large-scale system for the last 30 years and learned a lot of things. But this was back in 1984. That's a long time ago. That's 35 years or something. So back to creative programming. The thing is, I like to explore things by making fun things with it, because that's relatively risk-free, and I don't have to worry about not achieving the correct solution or something. I just make something for fun. And this kind of process, it fits really well with the principles of factoring. So when I read the Thinking Fourth book, I was like, this sounds useful to me. So usually when you do creative things, you start with something small. So instead of when you're trying to solve a real-world problem, you get something big, like make a text editor. That's hard to decompose because you have to spend a lot of time thinking about what kind of parts goes into this. But in creative programming, you just turn it on the head, you start with something small, and it's easier to work upwards from there. Then you add something you can tweak, because if you just write lots of instructions, you basically have a painting, and paintings are boring because they don't move, and moving things are more interesting. So you add tweakable parameters. And then you randomize or interpolate those parameters, because that's more interesting. Why would you make art with a computer if you can't randomize things? Because the computer can't make choices, only humans can. So, yeah. And then you have the last step, which is more multiply and iterate. And the thing is, like when you compare this to the factoring thing, you reach this kind of point where you start factoring your creative program and you make a new layer of vocabulary, so that you don't actually work with the low level, like drawing a lines and stuff. You work with entities instead, for instance. And this made it seem like this was a good fit. So here's the program from before. I'm going to try and factor this to make it something I can work with more. Okay, so we have the thing here, which we know it draws a square. So we can take this out, and we can define a new word, square, and square does this. Just going to format this, because that makes it look nicer. All right. So you can stick square back in here, and then we have the same program. We didn't have to fiddle around with parameters or anything, because it's a concatenative language. You can just chop out a bit of code and name it, and put the name back in. That's nice. And also here we have something. When doing rotations on the canvas, you have to move the center of rotation to the center of the canvas, and then move it back up after you've done the rotation. This is really cumbersome because you don't want to have to do this all the time, every time you want to rotate something. So we are going to take this out. Now the program becomes interesting again, but we find a suitable name for it, and stick the name back in. Now we have the same kind of function. And here as well, what we're doing here is shifting along the x-axis. And we can take that out and do the same thing here. We stick the name back in. Now we have something that it's easier to see what's actually doing. We have hidden some details away, and we can read this program more fluently. And this is the thing we use to achieve this kind of neon effect. So we can take this out as well, and make a new word called draw with neon effect. But here we see that the thing we have to do to achieve the neon effect is to draw something multiple times with increasing line width. So up here we have this part in the square definition, and this part doesn't really belong here. So we're just going to take that out and put it back here because it belongs to this function. Do here, we can do nice. So the program is looking better because spammers. This program now it's more obvious what it's actually doing. So we can do the same thing about some of the things up here. We see here that we have a color that's repeated twice. We don't want that. So it's also a color is likely to change. So maybe we take that out and just name it. Now we can just mention it here, here. And the thing is, these two lines, they actually belong to at least these three lines actually belong to the neon effect. You don't have to use them here. They belong here. And now we can see that we have something that, this is our program now. We set the stroke style to the color. We don't have to worry about what the color is, you just have the color. And then we draw 20 squares that are rotated around the center and shifted along the x-axis. Now we have something that's nicer to work with. We can do better. We can also extract some parameters here to play with. So you can start with the drawing of the neon effect. You can see that here we always draw a square. We don't want to do that. You can draw anything really, but if we take this out and we instead pass it as a quoted program to the draw with neon effect, you can then execute the quoted program once every loop. So here we take this function, will then read the quoted program from the stack, and it will execute it when it needs to. And because we are finished with the program after this drawing effect is done, so we can take it out. So now we have, we can put anything in here. We can draw triangles or circles or anything we want to. And the same thing about rotation. Here we always rotate pi ninths, and that's not, we don't want to do that all the time. So we take that out. Because the only thing that is central to the whole rotating around the center concept here is the 250 and 250 things. So we are going to put that in front of here instead. Now you can play with this value if you want to, like this kind of cool effect. And also here, shifting along the x-axis. Shifting how much? I don't know. Maybe you want to tweak that. So here we have a value that we can generate from a random sample from -35 to +35. You can just take that out and assume that this value is present when you invoke this program. So now we can maybe not shift at all. You can do this and we get back to this kind of clean star. It's nice. But there are some more parameters you can tweak, and I see that I still have time to tweak them. That's nice. For instance, in the square here, we have hard-coded it to be a square that starts at 100, 100 and is 200, 300 wide. That's very interesting. We want to be able to pass a width and the starting point to this function. So we are going to use some cheat codes. Because sometimes it's not practical to only work with concatenative style. Sometimes you want to use name state or variables. So we have an escape hatch that we can use. So we can see that we're taking the x and the y. So if now in where we invoke square here, we say that we want it to be centered in 250, 250. It will take those two variables and put them into variables here. And now we can mention those when we want to, instead of having to duplicate the state all over the place. But we also want to say something about the size of the square. So we want to say that we want a square that's 300 wide. So we're going to save that as W, like this. And now we just need a little hack here. This is to construct points. So now I can do x, y point. And it moves to that point. But the thing is, like, I wanted to pass in the center. So I get something that looks really strange. That's cool. But that's not what we wanted. We have to subtract or add the width so we get to the point where we want to be. So we're going to do something. Like this. This takes me to the place I need to be. And the thing is, this looks really strange. And repeating these kind of invocations gets tiresome. But the thing is, you're hiding all of that inside the square definition, so you don't have to worry about it anymore. As long as you get this part right, you can use squares all over the place if you want to. So let's do plus there and remove that. And if anyone's ever worked with, for instance, oops, that's completely wrong. Work with WebGL or something, they kind of recognize this, where you have to tweak all the things. It still looks kind of strange. Yeah, that doesn't matter. It looks cool. We can just jump ahead a little bit because I don't want to fix all of the things. So here we're back in with the thing we were trying to achieve. And now we can start working with things. And that's, if we rotate it by 4, maybe we want to have like a random width of the squares, like between 10 and 100. This looks kind of cool. 200, maybe we want 100, but we want more of them. 50. Yeah. So now we are able to draw futuristic-looking squarey patterns because we factored ourselves out of a bind, and we ended up with a vocabulary that was easier to work with. This kind of demonstrates the power of factoring and creative programming. All right. So the factoring is both enabled and necessitated by simplicity, because you can't, if you don't factor, you're going to get eaten alive by the need to always keep track of the stack. So you have to factor to get around that, but you also get superpowers factoring because the simplicity of the semantics of a language really makes it easy to extract functionality and name functionality and things like that. And also, it fits creative programming really well. Okay, some closing thoughts. Everything as a function is kind of mind-bending. That really messes with your understanding of mathematics as a whole. Like, you don't have values anymore, you only have functions. That's weird. Limitations help enforce simplicity by making you think more. Because you don't have always have values or something like that. You have to think more about how you want to approach a problem and how you want to solve your problem before you can actually go ahead and solve it. So that's nice. And also, creative programming is a really fun way to explore and learn. You don't have to worry about not solving your problem. You don't have to worry about doing it right. You only have to worry about, are you having fun? And that's nice. Here are some resources. The Thinking Forth book is available as a Creative Commons license on the internet, so you can get the PDF and read it for yourself, or you can buy it from Amazon. The Joy homepage contains links to papers written by Manfred von Thun, and where you can download the Joy binaries and stuff like that. And I would really recommend reading the paper about the theoretical foundation of Joy. because it really goes into depth with all these values as functions, and things like that. Michael Fogus, he writes a sign every now and then, and he did one on Forth, and it's really good. You should read that. There's an interview with Manfred von Thun where he explains why he designed it, design join like this, and the same kind of interview with Chuck Moore. Those two are interesting. There's a blog post series by some guy called Daniel. That's called Joy of Concatenative Languages, Part 1, 2, and 3. That's also really good. He also goes into like a simple type system for a concatenative language. And also there's a blog post called Why Concatenative Programming Matters, in the same style as Why Functional Programming Matters. It also explains a lot of these things. Slides and stuff. The language I used in my slides, I've implemented myself. It's called iterate. You can find it on my GitHub if you want to play with it. Also, the slides will be up on GitHub and also live on the internet after the presentation. The slides are live. You can go in and try the language yourself if you want to. And all the art and things is also in there. Thank you so much for listening. And if there are any questions and stuff, just grab me afterwards.